Hello, everyone. We are Secure by Teams, and at this moment, we will present our final project. Our project title is Federated Learning, Gradient Leakage Attack, and Privacy Defense. Our team members are Alim Misbullah, Laina Farsia, Stanley Ibrahim Adam, and Aurelio Naufal Effendi. In this project, we will investigate whether the federated learning truly protects user privacy, demonstrate a gradient leakage attack, and evaluate two privacy defenses, which are differential privacy and homomorphic encryption. This presentation is organized into 6 parts. First, we will explain the motivation behind privacy concern in federated learning. Second, we introduce our federated learning system and baseline implementation. The third, we demonstrate a gradient leakage attack. Fourth, we discuss differential privacy as defense. Fifth, we present homomorphic encryption for secure aggregation. And finally, we compare the result and discuss the privacy accuracy trade-off. Our project follows a complete privacy pipeline consisting of 4 major steps. Step 1 was building a federated learning system using federated averaging. The step 2, we apply a gradient leakage attack to demonstrate a privacy risk. Step 3, defend using differential privacy. And finally, the step 3.1, we implement the homomorphic encryption to protect model updates during aggregation. All project objectives were successfully complete. Each team member was responsible for a different component of the project. Although each member focused on specific component, we collaborate closely throughout implementation, experimentation, analysis, and report preparation. Together, we complete the entire privacy evaluation pipeline. Now let's discuss why this project is important. Federated learning is often considered privacy preserving because raw data never leaves the client device. However, recent research has shown that gradient and model updates may still contain sensitive information. An attacker can potentially reconstruct private training samples from this gradient using gradient leakage attack. Therefore, our main research question is, can private client data be recovered from model updates, and how effective are differential privacy and homomorphic encryption as defense? To answer this question, we conducted experiment using 3 datasets: means, fashion means, and GFAR10, representing increasing level of difficulty.
Okay, I will continue. First, let's review the concept of federated learning. Instead of sending raw data to a center server, each client train a local model using its own private data. Only model updates or gradient are sent back to the server. The server combine this update using federated averaging to improve the global model. A simple analogy is like a classroom. Students keep their notebook private, but send the improvement suggestion to the teacher, and the teacher combine all of the suggestion to improve the final answer. Next. Okay, this slide illustrates the federated learning workflow. The server starts by initializing a global model. Its client receive a copy of this model and train it locally using private data. The client then send model update back to the server. The server aggregate all update using federated averaging and update the global model. This process repeat over multiple communication run. Although raw data never leave the client, gradient are still shared, which creates a potential privacy risk. Next. For implementation, we use PyTorch version 2.5.1 with CUDA 12.1. We simulated 5 clients with non-IID data partition. Non-IID data partition means dividing the data set among different clients so that each client has different distribution of attack techniques. Its client trained for one local epoch per run. The baseline federated learning experiment used 5 communication run. For homomorphic encryption experiment, we used 3 run due to the additional computational cost. And the same CNN architecture was used for all dataset. The model consists of 2 convolutional layer, max pooling layer, and 2 fully connected layer, ending with 10 output classes. Using a single architecture ensure fair comparison across all dataset. Next. Before applying an attack or defense, we first evaluated baseline federated learning performance. MNIST achieved the highest accuracy at 98.79%. Fashion MNIST achieved 86.80%. And CFAR 10 achieved 53.06%. These results are expected because MNIST is relatively simple, while CFAR 10 contains more complex color images. This baseline accuracy represents the upper performance bound before applying privacy protection. Next. Although federated learning does not share raw data, Gradient may still reveal private information. The idea behind this, behind the deep lake from gradient attack is to reconstruct a private image from observed gradient. The attacker starts with a random dummy image. The dummy image is repeatedly optimized until its gradient becomes similar to the victim gradient. Once the gradient matches closely, the dummy image begin to resemble the original private training image. An analogy is reconstructing an object by observing only its shadow.
Okay, I will continue to explain about the illustrated how the DLG deep leak from gradient reconstruction attack works. So the process starts with the private training sample. From that sample, the attacker obtains the real gradients. Then they create a random dummy image and calculate its gradient as well. The goal is to make the dummy gradient as close as possible to the real gradient. So, through repeated optimization, the dummy image is gradually updated. As you can see, over time, the dummy image starts to look more and more like the original private image. In our experiments, the gradient descent dropped significantly across all datasets. For example, in CFAR 10, it decreased from around 6.9 to almost 0. This shows that gradient can reveal a lot of information about a private training data. So the main takeaway is that federated learning by itself does not fully guarantee privacy. Next. To defend against the gradient leak, we implemented differential privacy. So differential privacy protects client updates in 2 main steps. First, we use the clipping to limit how large its gradient update can be. Then we add Gaussian noise so that the exact gradient value are harder to identify. So the final protected update is the clipped gradient plus some added noise. A simple way to understand this is to imagine blurring a photo. The overall image is still useful, but the fine details become much harder to recover. In differential privacy, the privacy level is measured by epsilon. A smaller epsilon means a stronger privacy protection. Next. So differential privacy introduced an important trade-off. However, increasing noise strengthens privacy and decreasing epsilons. Adding too much noise reduces model accuracy. On the other hand, less noise preserves accuracy but provides weaker privacy guarantee. Therefore, selecting the correct noise level require balancing privacy and utility requirements. Next. So this slide shows the differential privacy accuracy curve. For MNIST, noise level 0.3 achieved the highest accuracy at approximately 90%. However, it also had the largest epsilon value, meaning weaker privacy. At noise level 1.5, privacy became much stronger, but accuracy dropped dramatically to about the 30%. We observed a similar trend for CIFAR-10s. The more complex dataset was particularly sensitive to noise because it relies heavily on detailed gradient information for learning. So next. So this is the complete differential privacy result are summarized here. For MNIST, increasing noise steadily reduced accuracy from 90.10% to 12.64%. Fashion MNIST achieved 46.67% accuracy with noise level 0.5. And for CIFAR-10s, accuracy decreased from 30% to approximately 10% as noise increases. So overall, this result clearly demonstrates the privacy utility trade-off associated with the differential privacy.
Okay, now our second defense mechanism to this attack, DLG attack, we tried is homomorphic encryption, which is also the step 3.1. So unlike the differential privacy, homomorphic encryption does not modify the update values. So instead, each client encrypts its update before sending it to the server. So the server performs aggregation directly on encrypted updates. Only the final aggregated results is decrypted. So an analogy for this one is probably like placing updates inside a locked box. The server can only combine the boxes without opening them. So only the final combined result is unlocked. We implement this approach through the 10-seal library. Next. So here is some comparison between the homomorphic encryption and differential privacy. So they both are quite different. They protect privacy, but in different ways. So for differential privacy, it adds noise and provide a formal privacy guarantee through the epsilon. So the accuracy decreases as more noises is added. So if we increase the epsilon, the privacy level will decrease, but the accuracy will increase, and also vice versa. But homomorphic encryption, it instead hides updates from the server without changing their values. So as a result, accuracy is generally preserved with using this method. But the trade-off is increased computation time due to encryption and description operation. So in summary, DP or differential privacy changes update values while homomorphic encryption hides update values. The main cause for DP is of course the accuracy loss, but the main cause for the HA is the computational time. So the choices depends on the desired privacy goal. Next. Now let's take a look at the result from the homomorphic encryption. You can see that for the MNIST dataset, it achieved 98% accuracy after only 3 rounds. Fashion MNIST also achieved 85, while the CIFAR-10 achieved 42.82%. When we compare it to differential privacy, the accuracy was preserved much better. This is more close into the real dataset, like without the attack. However, the encryption introduced some computational overhead, as we can see, like in the fashion MNIST dataset, it require nearly 20 seconds per communication round. So therefore, the main cause of this homomorphic encryption is additional computation time. Next. So this is the overall comparison. This slide summarizes all methods. Basically, the baseline federated learning achieved the highest accuracy and fastest training speed, but it provided limited privacy protection. While the differential privacy improved privacy through clipping and noise addition, but the accuracy decreased as noise increased. Meanwhile, the homomorphic encryption, it preserved the accuracy while hiding updates from the server, but it requires significantly more computation time. We also observed that the CIFAR 10 was the most challenging dataset and most sensitive to the privacy mechanism, unlike the other two, MNIST and the fashion MNIST, which is, we could see the dataset difficulty from each dataset. Next slide. Now, what are the key takeaways and conclusion that we can take from this experiment? So to conclude, first, the federated learning means full privacy. It only reduces data sharing, but does not automatically guarantee privacy. Gradients could still expose sensitive information. Second one, gradients can be reversed. Gradient leakage attack demonstrate that the private image can be reconstructed from gradients, especially for MNIST and CIFAR 10. Third, differential privacy provide formal privacy guarantees, but stronger privacy comes at cost of the lower accuracy, as we can see in the experiment. Fourth, homomorphic encryption, it preserves accuracy by encrypting updates, but still introduce some computational overhead. And finally, to conclude, there is no single best defense. So the best defense depends on goals. Like differential privacy is suitable when formal sample level privacy is required, but homomorphic encryption is suitable when update confidentially from the server is the main concern. So federated learning systems often need to balance privacy, accuracy, and efficiency. Next slide. So these are the reference that we use for this project. I think that's all from us. Thank you for your attention.